Okay, so we're continuing our discussion of Section 8.2 series. And in our last class, we talked about geometric and our harmonic series. So let me just refresh you. Let me go to the whiteboard, and you'll have a chance to copy this example. So a geometric series would be a series that can be written in this form. And the geometric series will equal A over 1 minus R. In other words, that infinite series will have a finite sum defined by A divided by 1 minus R if the absolute value of the common ratio is less than 1. So like for instance, for example, if you had this series, well, let me just write down a series. If you had this series, 1 plus a half plus a fourth plus a fifth plus an eighth, okay, and so forth. Okay, we could write that series as a series where n goes from 1 to infinity of 1 times some power to the n minus 1. What's the common ratio? What's the common ratio for this series here? What's the common ratio? 1/2, that's right. And so the sum of that series then, since 1/2, which is the common ratio, that's less than 1, the sum of the series is just going to be equal to 1, which is the first term, divided by 1 minus a half. It converges, yes. It converges, and it converges to 2. So that geometric series converges. That's an example of a convergent geometric series. Now, a harmonic series is another type of series. And that series is a series like this. This is a harmonic series, 1 plus a half plus a third plus a fourth, and so forth. And we learn that even though the terms of the harmonic series are approaching 0, they're getting smaller and smaller, still the harmonic series diverges. The sum will equal infinity. It's an absolutely amazing result. So we studied these two fundamental series from section 8.2, and we studied them, and now we hopefully have a decent understanding of them, and now we can explore some new kinds of problems. So let me just see here. Jonathan, if the absolute value of R is greater than 1, then the geometric series would diverge. That's correct. All right, so let me go back to our thing here, back to our examples. Okay, so here's an example. Now this series here is this series where n equals 1 to infinity of n minus 1 over 5n minus 1 is neither a geometric series nor a harmonic series, right? It doesn't, let me see here, hold on, there was a question. No, Jonathan, a harmonic series will never converge. Harmonic series will never converge. And incidentally, while I'm at it, let's say you had a series like this. Let's say you had a series like this, where n equals 1 to infinity of 1 over 3n. Okay? Because the 1/3 can be pulled out front of the summation sign, that's a property of summations, right? You can pull out constants. This series here can be written as 1/3 times the harmonic series. And so that series will diverge. So just be aware of that. Sometimes in the homework, that you're not always going to be seeing a harmonic series, like the series where you have 1 over n. You might have 1 over 3 to the 1 over 3n. But the 1/3, since like you can factor out the 1/3. And so you're taking 1/3 times a harmonic series. And that's like 1/3 times a divergent series. That's also divergent. Okay. All right, just want to mention that. All right, so let's see here. Now this series here, we want to know if it converges or diverges. So we could, of course, write out some terms of the series. We could write out some terms. All right, and I'm just thinking here. Let me ask you for large n, because what determines whether a series converges or diverges is how the series behaves as n gets large. Eventually the truth will come out, as they say. So when n is large, does the -1 here and the -1 here, do they affect the terms of the series that much? Do they? Yeah, they do not. They do not. I mean, you have to consider them in computing terms of the series. But the point is, for when n is large, basically the terms of the series are going to act like n over 5n, which is equal to a fifth. Okay, so eventually this series, effectively, it's going to be a series where you're adding terms that are all basically equal to a fifth. And if you add a fifth and 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 keep going, what are you going to get? Are you going to get a finite sum? No, you're going to get infinity. That's right. So this series, even without being formal in the solution, I mean, this series, intuitively, it seems like it would diverge. But now we can go and we can be formal here. And basically, being formal is really saying the same thing what I just said. If we look at the terms of the series as n goes to infinity, the terms are going to equal 1/5, right? The terms are going to equal 1/5. I mean, we could be a little more formal about it. I mean, if we have the limit as n approaches infinity of n minus 1 over 5n minus 1. Well, we can multiply the numerator and denominator by 1 over n. And so this will equal the limit as n goes to infinity of 1 minus 1 over n divided by 5 minus 1 over n. And clearly, as n gets large, these two terms go to 0. And so you're left with a fifth. So since the terms of the series approach a fifth, the series has to diverge by the test for divergence. That's called the test for divergence. And I have a note here to just think about how the series eventually behaves. So what I've done down here is I've written out the first 4 terms of the series. Okay, so we have, like this is first term, second term, third term, fourth term, okay. You know, the second term, how do we get a ninth? How do we get a ninth? That's easy. You know, you're taking 2 minus 1 divided by 5 times 2 minus 1, and you get a ninth. I mean, and then let's see here. Now here, this 4,999 over 24,999. What term is that? That's a sub what? That's right. A, if I heard right, a sub, hold on. A sub 5,000. That's right, Yonatan. That's right, Clea. And indeed, Mohammed, we can't pull out the 1/5. Well, hold that thought. Hold that thought. One moment. One moment. I'll get back to you on that. Okay, so this is the 5,000th term, and 5,000. I don't know why this keeps hitting this. Hold on here. Sorry. Hold on. Hold on. I don't know what's going on here. This crazy thing. Get this crazy thing off. Hold on. Let me get back to the. I'm telling you, man. Hold on. Let me get back to the example here.
So, Professor.
I think I know what to do next time. I'm just going to hit. There's an X button on the right. I don't know why that ever would show up. You know, who would want that? Hit the wrong button and that shows up. Come on. One moment here now. One moment. I know. Let me just see. I got to start right from the. Let me. I know we have a few questions, but let me just complete my thought here. Hold on, Clea. Hold on, Mohammed. I haven't forgotten you. I haven't forgotten you. Okay. So again, let's think about this very, very simply. Our series, okay, the first 4 terms, okay, are the first 4 terms. It's not easy to see that those terms are, you know, but what are the terms approaching? Well, you have to go out to, you have to let n get big, like the 5,000th term here. The 5,000th term is 4,999 over 24,999. And then the 5,001st term is 5,000 divided by 25,004. Now, if you take 5,000 and divide it by 25,004, you're going to get something very close to a fifth. So the terms, basically, the terms are behaving, the terms are approximately going to be equal to a fifth as you move out into the series. And it's like adding 1/5 infinitely many times. And that's why the series is equals infinity. And that means our series diverges. Now let me see. Mohammed was asking about at the top here. Mohammed, you can't factor out like up here, factoring out a fifth here. You can't. You can't factor out a fifth because you have the minus ones here. So you can't factor out a fifth. It won't do anything for you. Okay, and you can't really do it. So that, all right, Mohammed, all right? Okay, good. And Clea, excellent. Clea, what's your question?
Yeah, so I'm seeing with harmonic series, usually they diverge. So like this is true for all harmonic series, or?
Well, this series here, if you think about it, there's another way to. This isn't really though a harmonic series. This series is this is not a harmonic series, as a matter of fact. It's a series where the terms of the series are basically approximately equal to a fifth. as you move well into the series. So it's not a harmonic series. It's just a series that where the terms are approximately equal to a fifth as you move out into the series, and therefore, if you add a fifth an infinite number of times, you're going to get infinity. So it's not a harmonic series. It's another type of series, but it's a series that we can say diverges. And you want to be careful, of course, in your homework for section 8.2, because some of the problems, like does the series converge or diverge, and it's multiple choice. It's either right, one chance to get it right. So you want to definitely take the time before you just click the button, but all right, Clea. All right, is that I think if we see
Yep.
enough examples, all right, good. If you see enough examples, you'll get more comfortable. So let's look at another one here. Are there any other questions before we move to the next example? Okay, then let's move to the next example. Now here, I'm going to give you a moment to copy this example down. Okay, so all right, this is an interesting looking series. It's a series of a sum. It's a series of a sum. Let me ask you this. If you have a series like this, okay, and I can put n equals 1 to infinity here. Could we rewrite that series? Well, could we rewrite that series as some other, like, how could we rewrite this series? It's a series where you have the sum of two terms. Yonatan?
You could just separate it saying the sum of 4 over e to the n plus the sum of 3 over n plus 1.
Well, that's right. And you're utilizing this rule that I'm writing up here. Very good. So intuitively, it makes sense that we could take a series of a sum of two terms and just have the sum of the two separate series. And we can do that for here as well. Okay, so let's go to the solution and see how this works. Okay. So again, you have the, this is AN, this is BN. Okay, so, and here's AN and here's BN. So indeed, we can rewrite the series of the sum as the sum of the two series, right? We can do that. And constants like 4 can be brought out in front, 4 and 3 can be brought out in front of the series. So that gets me down to here. Please let me know if you have any questions. Okay, so we're down to here, and we have two series that we need to evaluate. Okay, two series that we need to evaluate. Now, first what we want to do is we want to see if this series here converges. Okay, does this series converge? And if it converges, then we have to look at this second series here, which is an interesting series. Does that
So,
series converge?
so Professor, we look this just like separate.
We do. We do.
Uh,
Yep, that's what we have to do. But you know, the first series is actually a series that you're familiar with. It's a convergent geometric series because you know 1 over e to the n. Okay, this can be thought of as like 1 to the nth over e to the nth. And so that gets me then to this series here, series where n goes from 1 to infinity of 1 divided by e to the nth power. And I write out some terms of the series, and this is just what is this? This is just a convergent geometric series with a common ratio of 1 over e. So the common ratio of 1 over e, let me see here, I might need a little more space. Just give me a moment here. All right, so let me just make a comment here. So the common ratio is the absolute value of the radius is just 1, or is itself, because and 1 over e is less than 1. Okay, because e is the Euler's number, and that's greater than 1. As a matter of fact, let me see here. Euler's number, if you like type like e to the first power on your calculator or in Desmos, e is base e is approximately equal to 2.718. How many remember that maybe from their pre-calculus days, seeing that? The Euler's number E. Well, all right. Well, now you're seeing it, and so it converges to the finite sum, and this is the, you know, a divided by 1 minus the common ratio. Common ratio r is 1 over e. And what we can do here, if we want to make this fraction look a little nicer, is, let me see here, I think I'll erase this here. Yeah, if we multiply top and bottom by e, okay, and then you distribute on the bottom the e to the 1 and the e to the 1 over e, you will get this as your answer. So that's the sum. That this first series converges to equals 1 over e minus 1. Hold on, there was a chat message here. Well, yeah, Mohammed, we will be dealing with those constants. We can't forget about them. First thing we want to see is if the series converges. But then a natural follow-up question is, well, all right, if the series converges, what does the series converge to? What number? And when we compute that number, we won't forget that there was a 4, that there was a 4 here. Good question, good question. All right, well now the next series we have to deal with is this series here. Series where n goes from 1 to infinity of 1 divided by n times n plus 1. And this is a special series that we're going to call, the book calls this a telescoping series. So the series is neither a geometric nor a harmonic series, but it's what's called a telescoping series. And we want to see if that telescoping series converges or diverges. So let me go to the next page and I'll show you how we do this. Are there any questions? All right. All right. So let me give you a moment to copy down to here, and then I'll talk about what you're seeing, okay, regarding our telescoping series. Okay, so, all right, how are we going to deal with this particular series? So what I did was I wrote out some terms of the series just so it's a little less abstract. And it turns out we can think of this as a telescoping series. How are we going to show that it converges? What we're going to do is we're going to look at the nth partial sum of the series. Okay, the nth partial sum is the sum of the first n terms. So like if we had 1 over 1 plus 1 plus 1 divided by 2 times 2 plus 1. Okay, those are the first 2 terms of the series, right? All right, and then we kept adding terms and stopped our sum at the nth term, where the nth term is n times n plus 1. That's called an nth partial sum because it's the sum of the first n terms of the series. Now, what we want to do is we want to write this nth partial sum. We want to rewrite this in a nicer way. Okay, and oh my goodness, what's this? I'm taking 1 over the I times I plus 1 and writing it as a. See, we have 2 linear factors on the bottom, the I and the I plus 1. And I'm writing that as a divided by I plus b divided by I plus 1. And then I'm going to solve for a and b. What are we doing here with this? What is that called, this procedure that we're doing here? Begins with a P. That's right. Good, Yonatan. Partial fractions. Partial fractions. Okay, and so what we're going to do, right, if you remember partial fractions, we're going to multiply both sides of this by I times I plus 1, the common denominator. And then that's going to get me the second statement below, that 1 equals A times I plus 1 plus B times I. And you just continue working through the partial fractions. You've done this process before. And it turns out that, well, A plus B, 1 is equal to 1 plus 0 times I. So A plus B has to equal 0, and A has to equal 1. Therefore, B is negative 1. So we're able to take this partial sum here, this nth partial sum, and rewrite it, in another way. And I'll show you that on the next page. But are there any questions right now on this? Are there any questions? Yes, Clea.
Can you just explain, please, the part why A plus B equals 0?
Oh, well, so in this equation here, you have A plus B times I plus A equals 0I plus 1. So since both sides of this equation are equal, the constant A would have to equal the constant 1, and so A equals 1. And then the coefficient of I, A plus B, would have to equal the coefficient of I on the left, which is 0 times I. Hence, A plus B equals 0, A equals 1. If A equals 1, then by virtue of this equation here, A plus B equals 0, B would have to equal negative 1. Does that, so you've done this before. You've all done partial fractions before. You've done even ones more complicated than this. But does that help refresh your memory, Clea?
Yes.
Okay, good. All right. Well, are there other questions, or shall we just we'll just move on here? All right. Well, let's move on. So, hold on, Mohammed. I'll do your best, Mohammed. Thank you for letting me know. Okay, just do your best. Thank you. All right, you're welcome. So, okay, I'm going to rewrite now, this partial sum. Okay, this partial sum here, the nth partial sum, that's what this is. It's the nth partial sum because it's the sum of the first n terms. I'm going to rewrite that this way because 1 is equal to A, and the negative 1 is equal to B. Okay, so, partial fraction expansion. And then what I'm going to do is I'm going to write out some terms of the series. So let me give you a moment to catch up here. Okay. So, all right. So here's our nth partial sum. Here it is. And so the first term here is when I equals 1. Second term is when I equals 2. Third term is when I equals 3. The fourth term here is when I equals n. See, I goes from 1 to n. Are there any questions on that? Are we okay with that? All right, well, what seems to happen here? Is there any simplification going on? I mean, if we were just to sort of look at like let's say we looked at S sub 2. S sub 2 is 1 minus a half plus a half minus a third, right? Do any terms cancel out?
If we do it this way, then it will cancel out to 1 plus the last term.
That's right. You got the negative half and the half cancel. The halves cancel. That's right, Shalom. That's right, Yonatan. And what you're left with is you're left with. Oh man, hold on. I'm hitting up. Now hold on here. I hit one of these crazy buttons again. Forgive me. Just give me a moment here. Doggone it. Hold on here, class. Oh, maybe you can help me. I hit a button I didn't want to hit. And it's giving me, okay, good. Okay, I just hit that. I mean, clarification, please. I like to know what's going on. I hit the wrong button and it kind of gets me upset. I mean, it doesn't hurt to have a clarification. But I'm very pleased with the new system we have. But maybe something like unclick this if you don't want that. I don't know. But let's just continue here. So 1 minus a third. Now that equals 1 minus 1 over 2 plus 1. So the second partial sum equals 1 over 1 minus 2 plus 1. Okay. If we look at the third partial sum, I think I can fit it here. The third partial sum is equal to 1 minus a half plus a half minus a third plus a third minus a fourth. Do any terms cancel out there?
Can we cancel 1/2 and 1/3 since they're repeating?
That's right. That's right, Clea. That's right, Yonatan. So you see, the sum is a telescoping sum. So a telescope, opens. I'm sure you've all seen a telescope like the sailors used to use, or maybe still use, where it expands. How many have seen that maybe in the movies, a telescope, the sailors using the telescope to spot ships and other ships? Master and Commander, the movie. I don't know if you've seen that with Russell Crowe. But collapsing telescopes. That's right, Jonathan. So you see, what happens then is S sub 3, that third partial sum can be just thought of as 1 minus a fourth, but that just equals 1 minus 1 over 3 plus 1. You see? So the general pattern here that we're seeing with the nth partial sum is that the nth partial sum will equal 1 minus 1 divided by n plus 1. You see? And so now, if we want to look at the limit of the nth partial sum as n goes to infinity, okay, that would be the same as looking at the limit as n goes to infinity of this, telescoping nth partial sum. And that's just going to be the limit as n goes to infinity of 1 minus 1 over n plus 1, but that's just 1 minus 0. And so you get a 1. You get a 1. And so this means then that the series, hold on here, I want to make sure I have it. One moment, class. Our series I think I can fit it in over here. So our series, and they come up a lot. They come up a lot. If you go on in math, you'll see these again. This series, the summation just equals 1. Because the limit of the nth partial sum of the series is equal to 1. So the series converges, and the sum of the series is 1. So that was another way we can establish if if the series converges, we can find its sum by looking at the nth partial sum and finding the limit of the nth partial sum. And in this case, the nth partial sum does have a limit. It equals 1. And so the series equals 1. Okay, and now we're ready to get to our final answer. So we've established that that second series equals 1. And now, as Mohammed said, we have to now worry about, we have that, the constants of 4 and 3. So remember what we did. One moment, let me just, hold on. Remember, we had that this series was equal to 4 times this series plus 3 times this series. And so now that will equal, what? Well, we established that this series here is 1 over e minus 1. And the second series here equals 1. And so we get down to here. And WebAssign would take this answer. I mean, this answer this answer here is perfectly acceptable. But we could do a little rewriting and write the sum as, you know, what you see below as well. So the sum of those two series converges, and that sum would be 1 plus 3e divided by e minus 1, which is a positive sum, right? It would make sense. The terms of both of those series are positive. So the summation has to be positive. The sum has to be positive. Series converges. All right, are there any questions on that problem? Who's feeling good? Who's feeling reasonably good about what they're learning today? Who's reasonably comfortable? Okay, Clea, excellent. Good, excellent, Susanna, excellent, Victoria. Okay, good, good. All right, well, let me stop the recording here for this here, if we're good. Excellent.